So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamualaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. So today we are going to start section 4.5, that is electromagnetic effects. An e.m.f. or electromotive force will be induced in a conductor if there is a relative movement between the conductor and the magnetic field lines. It will also be induced if the conductor is stationary in a changing magnetic field. So if you want to produce e.m.f. in a conductor, then there are two ways: either keep the magnetic field stationary and move the conductor inside that field, or either keep the conductor stationary and move around the magnetic field or change the magnetic field so that the magnetic field lines keep on changing or varying. For an electrical conductor moving in a fixed magnetic field, the wire or the conductor would cut through the field lines, and when this happens, the magnetic field lines would induce the free electrons inside that conductor to move, and once the electrons would start to move around, as we know, the movement of electron is known as current. Hence an e.m.f. would be induced inside that conductor, and this thing can be demonstrated by the following experiment. A straight wire is held at rest between the poles of a U-shaped magnet. It is then moved in up, down, right, left, forward and backward directions, and the voltmeter connected to the wire is observed. Only when it is moving up or down, the voltmeter would show some deflection, meaning that the detection for an induced e.m.f. The deflection is in opposite direction in these two cases and only lasts while the wire is in motion. This would be the diagram for it. If you move it upwards, if the meter is deflecting to this side, then moving it downwards would deflect it to the other side. A bar magnet is moved between a coil of wire. As the magnet moves through the conductor, the field lines cut through the turns on the conductor. This induces an e.m.f. in the coil. A sensitive voltmeter can be used to measure the size of the induced e.m.f. If the conductor is part of a complete circuit, then a current is induced in the conductor, means whatever load you have connected to the circuit would light up. This can be detected by an ammeter. and this would be the setup for that. Now over here it is shown a galvanometer. As I have previously mentioned as well, galvanometer is simply an ammeter that can detect the very slightest change in current as well. Factors affecting the size of an induced EMF. There are 3 factors, and this was concluded by Faraday. That induced EMF increases if you increase the speed of the motion of the magnet or coil, the number of turns on the coil, or the strength of a magnet. These are the only 3 ways in which you can increase the induced EMF in a conductor. Lenz's law. The Lenz's law states that the direction of an induced potential difference always opposes the change that produces it. It basically means if you try to put in a bar magnet, the north pole of a bar magnet inside a coil, then this part of the coil would turn into a north pole of its own, and it would repel the magnet. And when the magnet is moving away, then due to the change in magnetic field, the poles of the induced current would be reversed, and hence a south pole would be created over here. As you can see, right now the field lines are going in that direction, and now they are going in this direction, and now that it becomes a south pole, it is going to attract the bar magnet. So basically, whenever a current, an EMF, a potential difference is induced into a coil or a conductor, it would always be in such a direction that it is going to oppose the source that created it. If a bar magnet or a permanent magnet is used to induce that current, that potential difference, it would always become or turn itself into having a magnetic field, having a pole that would repel the nearest pole of the bar magnet, as demonstrated in this diagram. So any magnetic field created by the potential difference will always try to stop the wire or magnet from moving. Now, how you can demonstrate the Lenz's law? If a magnet is pushed north and first into a coil of wire, then that end of the coil would also become a north pole. Explanation: due to the generator effect, means due to the fact that you are moving a magnet inside a coil and the field lines are being cut, that is going to produce induced current. A potential difference will be induced in the coil, which will always oppose the change that produces it. The coil will apply a force to oppose or push away the magnet being pushed into the coil. Therefore, the end of the coil will become a north pole, and it will repel the north pole of the magnet. If a magnet is now pulled away from the coil, then that end of coil would become a south pole, so it can attract it. And this would happen due to the generator effect. The induced PD will always oppose the change that produces it. The coil will apply a force to oppose the magnet being pulled away. Hence, that corner of the coil, that edge of the coil, that end of the coil would turn itself into a south pole, so it can oppose the motion of the magnet and pull it back. Fleming's right hand rule or Fleming's dynamo rule. If you hold your thumb and the first 2 fingers of the right hand at right angles to each other in this position, Fleming said that the first finger would always point towards the direction of the magnetic field, the second finger will point towards the direction of the current, and the thumb will point towards the direction of the motion or the direction of the force for the movement of the conductor. Like we just said, the movement of the conductor over here, like over here the conductor was being moved. The direction of the induced EMF always opposes the change that produces it. So any magnetic field created by that EMF will try to stop the wire or magnet from moving. In such situations, we can use the Fleming's right hand rule to find the direction of the magnetic field in a coil wrapped around a solenoid. How you can do that? Simply point the wrapped fingers, curved fingers, turn the fingers along the coil and in the direction of the conventional current. The direction of the conventional current is always opposite to the direction of flow of electrons, from positive to negative. Then the thumb will point to the direction of the magnetic field within the solenoid. If you wrap your fingers around a coil like this, so that your fingers are curling in the direction and your thumb is straight. If you align your thumb with the direction of the current, then the curling of your finger, the direction of the curl of your fingers would give away the direction of the magnetic field produced by that current carrying conductor. Example question: a wire is placed in the magnetic field between the poles as shown. Now we are not being told that which pole is which. When there is a current in the wire, it experiences a force. Which change increase the size of this force? Reverse both the direction of the current and the poles of magnet? No. Faraday's rule says this would not cause any change. It would not cause any increase. Reverse just the direction of the current? Again no. Use a stronger magnet? Yes. You can use a stronger magnet. You can increase the number of turns, or you can increase the speed of motion. Figure shows a horizontal current carrying wire PQ in the gap between two poles of a permanent magnet S and N. There is a magnetic field in the gap. The current in PQ is from left to right, from here to here. Describe the effect of magnetic field on PQ. It will produce a force in wire PQ, causing it to move. Now in which direction it would move? You will have to apply the right hand rule. If you apply the right hand rule, that means thumb is towards the force, first finger is towards the magnetic field, and the your second finger should point towards the current. So your second finger should point towards Q. Your first finger should point the magnetic field lines originate from south and go towards north. So your first finger should point downwards. In that position, your thumb will point to yourself. So it means the force in the wire PQ will cause it to move sideways or out of the page. State the effect on PQ of increasing the strength of magnetic field. Force produced on PQ will also be greater if the strength of magnetic field is increased. Figure 7.2 shows part of a torch. The torch does not have a battery. It is shaken, and this causes the magnet to move backward and forward inside the coil. Explain why an EMF is induced. When the magnet moves through the coil, the magnetic field lines are cut, causing the coil to have an induced EMF. State one way to increase the EMF. Increase the number of turns. Use a stronger magnet. Shake it more violently. As the magnet moves, the induced EMF produces a current in the coil. Explain how this opposes the motion of magnet. When a current starts to flow in the wire, it produces a magnetic effect of its own, causing the coil to have magnetic poles. According to Lenz's law, this will cause the right side of the coil, this one, to turn into a north pole. Why? Because north pole is closer to it, repelling the north pole of the coil. Since this is just for 2 marks, so this much explanation is enough. Next we have the AC generator, or the alternating current generator. It is an electromagnetic device which transforms mechanical energy into electrical energy. It consists of a rectangular coil of wire which can be rotated about an axis. This coil is located between the two poles of permanent magnets. As the coil rotates, the magnetic field through the coil changes, which induces an EMF between the ends of the coil. The induced current does not flow unless the generator is connected to an external current. Means if no matter how much you turn the generator, if you have not connected it to an external circuit to some load, the current will not flow. This is the diagram for an AC generator. Here is the rectangular coil, here are the two poles, these are the carbon bushes, and this is the load, or and these rings are known as slip rings. They rotate with the coil. The purpose of the slip ring is to allow the transfer of EMF induced in the rotating coil to the external circuit. Each ring is connected to one end of the coil and is electrically connected to the external circuit. Like as you can see, this end is this coil is connected to this end of the circuit by the use of carbon bush, and it is connected to this wire CD, whereas this slip ring is connected to this end of the circuit and it is connected to the second wire of this rectangular coil. The difference between AC generator and DC motor is the use of a split ring. The DC motor uses a split ring commutator, which reverses the current direction in the coil every half a turn and allows the coil to always turn in the clockwise direction. This we'll discuss later on in the DC motor topic. Now here is a diagram or graph of what happens when a AC generator is turned. This is the direction of the rectangular coil, and this is the graph of current that is produced when it is turned at a 360 degrees, from 0 to 360 degrees. The coil is being turned in a clockwise manner and the magnetic field is pointing towards the right. Now what happens is that at the reference position 0 degrees, the plane of the coil is perpendicular to magnetic field. As you can see, the sides of the coil are moving parallel to the magnetic field and not cutting through it, so no EMF is induced. Then the coil is turned to reference position 90 degree. From here it is moved to here. Now the field lines will be cutted through by the coil is cutting through the magnetic field lines at the greatest rate, so maximum induced EMF is produced. As you can see, the maximum amplitude for the induced EMF is reached. And once again, when the coil is turned to another 90 degrees and it again becomes parallel to the magnetic field lines, no EMF is induced and it is at 0 degrees or zero voltage. Then when it is turned again at another 90 degrees, it becomes equal to this part. This time the maximum, however, since the direction has been changed, so the polarity or the direction of the induced EMF is also reversed. Hence now we get a maximum amplitude on the negative side. And lastly, when we again turn it to another 90 degrees, it becomes the same as the first position, so no induced EMF is produced as no field lines are being cut by the coil. Ways to increase EMF in AC generator: decrease the distance between magnet and coil to increase magnetic field strength, use a stronger magnet, increase the frequency of rotation, double frequency equals to double maximum EMF, increase number of turns in the coil, double number of turns would become double induced EMF. Example question: a rectangle current carrying coil is pivoted between the poles of an electromagnet. Which action does not increase the size of turning effect exerted on the coil? Increasing the current in the coil? No. Increasing the current in the rectangular coil? Obviously not. Reversing the current in the electromagnet? It would not cause the coil to turn, or it would not cause the coil to be pushed away or to be moved. Increasing the number of turns on the rectangular coil A, B and C would cause greater turning effect or greater force, because these A, B and D points would cause greater induced EMF, whereas only C would have no effect on the size of the induced EMF, hence the turning effect would not be increased. There is a current in the coil in the direction shown. Here is the direction shown. It is flowing from Z to Y, Y to X, and then X to W. Which statement is correct? The side WX experiences an upward force. Now over here you'll have to use the left hand rule to deduce the direction of the force. Now left hand rule would come ahead in the syllabus. Let me briefly describe it. Just like the right hand rule, the left hand rule states that if you position your thumb, first finger and second finger in such a way that all three of them are at 90 degrees angle to each other, then in that case your thumb points towards the direction of the force, your first finger points towards the magnetic field, and your second finger points towards the direction of the current. Over here the direction of the current is from X to Y, the direction of the magnetic field is from north to south, and hence your if you position your left hand along with this diagram, you will see that your thumb is pointing towards your roof, your ceiling, or is this pointing upwards. So hence the answer would be A. Okay, so that's it for today. I'll see you guys in the next lecture. If you have any problems, do tell me in the comments. I'll see you guys in the next class. Take care. Allah Hafiz.